Hello everybody, welcome back to another episode of the problem solving series. Today we are going to be talking all about inclined planes. Take a breath. Everybody hates inclined planes. They're the worst. They're not that bad. The picture is hard. Drawing the force diagram is a little bit more difficult. There's just a little bit more thought that has to go into it, but I'm going to go ahead and break it down for you guys. I'm going to show you two different ways that you can think about breaking up the forces and explain the direction of motion, and then go through some examples as per usual. I'm going to do two examples in this video, so I'm going to do one with no friction, so just dealing with normal force and gravitational force and how those come into play when you're on an inclined plane. Then I'll go ahead and throw in friction in the second example. The only other variation of an inclined plane that I think that you guys would want to study and take into account and that you'll most likely see is if you were to have tension, so something also pulling or pushing. But usually when you have tension like that, that is connected to another mass. So I'm going to save that for the pulleys problem video, just so that you can see a little bit more complicated example in there, and I think that it fits a little bit better, and that way this one is a little shorter. So we'll start from first principles. I'll explain some of the steps and how I used what I explained in the forces video, so go back and watch that if you haven't gotten to see that one yet. And yeah, well, let's get into it.
Okay, the first case of inclined planes that we're going to look at is going to be the simplest case, no friction, no tension, just good old normal force and gravitational force. So we have a box of mass 1 kilogram sitting on an incline of 30 degrees. What is its acceleration? In general, for force problems, the steps that you're going to want to take is we're going to draw the free body diagram. Then you're going to use the equations above, which I'll just call F net equations, maybe some second law, depending on if you have more than one object and you need to set those up. And if they're not already broken up, obviously the intermediate step that would go there is that you need to break up the vectors into the components that you're going to sum along. And then usually once you have those F-net equations set up, you're good to go ahead and substitute and solve. Yay! So let's go ahead and follow those steps here. So I'm going to draw this. So this is our incline. This is our 30 degrees. And I'm just going to draw the box as a dot, so that way we could draw our forces on here. And I'm going to really exaggerate the forces because it's so easy to mess up this picture and it gets cluttered very easily. So I'm just going to draw it really big for you guys. So FG should always be pointing vertically down. So we've got FG there. And then normal force, remember, has to point perpendicular to the surface and away. So perpendicular to our surface would be going at this way, and that's going to be our Fn. So now what we're going to have is, because this box is not going to be, if you put a box on an incline, it's not like it goes flying off in the vertical direction. The acceleration is going to be going down the ramp this way. So what we're going to want to do in order to use our force equations is we have to break up the gravitational force into a perpendicular component to the incline, similar to how the normal force looks, and those two will balance each other out, as we'll see, and a parallel component. So the perpendicular is going to go like this. It's not drawn to scale. FG perpendicular. So I'm just going to put out the side note. This symbol stands for perpendicular. And then this symbol of two lines next to each other stands for parallel. So we're going to have that component perpendicular, we'll have this component parallel, and then I'm not going to prove it here because honestly I forget how you do prove it, but this angle from congruent triangles is also 30 degrees. So once we have this, and then the other thing I just want to do right below it, the other way that we can think about this that I've seen some textbooks do is they'll draw a little XY axis that's been tilted, X and Y, and then they'll go ahead and call those components instead FG and Fx, just so that it's a little bit more consistent with the fact that the equations you're given are summed along X and Y. And the other thing that you can gather from this is so we can always really pick which way is positive and which way is negative as long as it's consistent throughout. But because of the things that we're used to, we always call to the right positive and up positive, or, to the left negative or down negative. But now we have kind of this weird situation where it's really up to our discretion what we want to choose. So by writing the axes this way, we're saying that down the ramp is going to be the positive direction, which means up the ramp would be negative. So I'm just going to put a little positive and negative there, and that is typically the convention. So most problems you'll see they'll call them down the ramp is the positive direction. Okay, so once we have that, I'll go ahead and use the perpendicular components, but we can say using trig functions, so this would be FG perpendicular equals FG times cosine theta, FG parallel equals FG sine theta. We'll use our sum of our forces in the y equals 0, since AY is equal to 0, so technically this would just be an AX or an A parallel. And we have positive normal force minus FG perpendicular equals 0. So normal force equals FG perp if we add that to the other side. And for now, I'm just going to leave that as FG cosine theta. If we wanted to go further, we could. We don't really need that for anything in this problem, but we'll use it in the next one for friction. Then for the sum of the forces in the x, that's going to be equal to our MAX. And then the only force we have going on parallel right now is going to be that FG parallel equals MAX. We'll substitute in the expression we just found for parallel. So that's sine theta guy. And then, so the other equation that I didn't write down is just that the force of gravity is equal to mass times gravity. So then we could put that in for FG. So we'll have mg sine theta equals max. So that's the last of our substitutions. Now we can actually start to cancel some stuff. So we have an m on both sides, which means that those guys cancel. And then we can put in 9.81 sine 30 equals ax. Sine 30 is a half. So if you want to go ahead and you could plug this into a calculator, but we will get 4.95 meters per second squared is our acceleration. Now let's look at a problem that does have friction, so we could see how we would use the sum of the forces in the y, like I referenced it before, and how friction comes into play. So we're going to have the same exact setup, but now I'm asking what does the coefficient of friction need to be to keep the box on the incline and to not move. So basically all that that's saying is that our acceleration is now equal to 0 completely in the x and y. I guess I'll write the mass as 1 kilogram just so we have a list of givens. Just didn't want to redraw the picture, but generally you would have to go ahead and redraw this picture again. But now we're going to add on friction. So since gravity is trying to pull this down, friction is going to be opposing that motion. And this is going to be static friction, so I'm going to write little fs. So we already broke those guys down, and they're down there, so then we're going to set up. So I'm going to first set up the x equation. So sum of forces in the x equals 0. Since our a is 0, I'm choosing downward to be positive, so we're going to do Fg parallel minus friction equals 0. Fg parallel is Fg sine theta. The equation for the frictional force, and I guess I should mention, since I didn't talk about this specifically, this is going to be the max, since technically for static it's less than or equal to, but our max frictional static force is mu s times normal force. So then we can go ahead and put in mu s normal force there equals 0, but we don't know normal force, so that's what we would get for F from the sum of the forces in the y. So that's what I was trying to hint at in the first one. So I'm going to go through these steps a little bit more quickly since I already did it in the previous example. Say, oh, what am I doing? Maybe I shouldn't because I made a mistake. So Fg perpendicular equals 0. Substitute Fg cosine theta equals 0. Add that Fg cosine theta to both sides so that we get Fn equals Fg cosine theta. And then I'm going to leave this here. And then this whole expression that we just found for Fn is what we're going to put in there. Then we'll have Fg sine theta minus mu s Fg cosine theta equals 0. Going to add mu s Fg cosine theta to both sides. I'm going to run into that Fg cosine theta. Scroll down a bit. So we'll have Fg sine theta equals mu s Fg cosine theta. So our Fg's are going to cancel. And then I'm going to show you the other trick that typically happens in these types of problems. So now we're left with a sine theta equals mu s cosine theta. If we divide the cosine theta out, so we'll divide both sides by cosine theta so that these cancel. If you remember, and I don't know, this might not be something that's on your equation sheet, but general trig identity that's good to know is that sine theta over cosine theta is equal to tan theta. So once we have that, substitute tan theta in for that fraction. We can plug in that last 30. It's going to be 0.58 is mu s.
And there you have it. So that's all. That's my take on inclined planes and how to work through doing those problems. Obviously, I did kind of simple examples, but hopefully it gets the point across for how you apply Newton's laws and the forces concepts to inclined planes. And like I said in the intro, there will be another inclined plane problem in combination with a pulley problem or like a connected mass problem. in the pulleys video. That should be the next one that I put out. So until then, happy physicsing, and we will go to Howitzer for our outro trip. Bye.
Hey! You gonna say bye to the kiddos? Can you sit? You sit? Look at how pretty you are!